Hello guys, welcome back to my YouTube channel Gamma Di Gamma. So in this video, I'm sure you're aware, I have an entire playlist on differential equations, and therefore I wanted to actually explain a really useful tool in differential equations, that's Laplace transforms. You may be familiar with Laplace transform. I'm sure you're familiar if you're an avid viewer of my channel, but in any case, we're going to do an application part of that concept. That's why let's get started. Okay, so for a general recap, if you guys have forgotten, the Laplace transform, which we denote by this curly L, of a function of t is the integral from 0 to infinity of e to the negative st f of t dt, which we can denote as capital F of s. The way I see this is, instead of having a function of t, you can have any other function, but this the power of e, the variables are, leaving the negative aside, the t is the input variable and the s is the output variable. So we need to have this fixed. So because if I have a function of x, I do that, I'll have to have e to the negative sx if I want to have an input of x and an output of s, denoted by this capital F. Okay, so that's the formula. It's really useful for some forms of integration. I think I had an entire playlist on this. Anyways, just check that out. Okay, so now the idea is we have a function of x and we need to find the Laplace transform of the function of x. So what we do, we just write that instead of a general function of f, we have the nth derivative of f of x. Okay, so I mean, we can just write that as an integral from 0 to infinity of e to the negative sx. I want the output to be s and the input to be x, and the nth derivative, which I can denote as d to the n over dx to the n of f of x dx. Okay, now what I can do is I can just use some integration by parts, because I can actually find the antiderivative of this guy while I am actively differentiating this guy. So I'm sure by now you're fluent with integration by parts. So we'll have the n minus 1th derivative, because the antiderivative of a derivative will be just removing one derivative. So I'll represent it as d sub n minus 1 of f of x, along with this e to the negative sx term, evaluated from 0 to infinity, minus integral from 0 to infinity. Now the derivative of this guy is negative s, and the same thing, e to the negative sx, and we have the n minus 1th derivative of f of x dx. Fair enough. Okay, so at infinity, this exponential is going to decay so hard that whatever this f of x is, whatever the n minus 1th derivative of f of x is, an exponential decays the fastest. So the denominator will become really heavy and it will all go to 0. But at 0, e to the 0 is 1, and we just are left with negative n minus 1th derivative of f of x at x equals 0. Okay, and this guy, if you just look at the formula we have above, is the Laplace transform of the n minus 1th derivative of f of x. So if I didn't know any better, I would say this is a recursive relation, because this is nothing but the Laplace transform of the nth derivative of f of x is nothing but negative n minus 1th derivative of f of x at x equals 0 plus s times Laplace transform of n minus 1th derivative of f of x. Sounds crazy, but I mean, if we can continue to do this process now, because now if we bracket this, we will just end up with negative the n minus 2th derivative of f of x at 0, by the same logic, plus s times the Laplace transform of the n minus 2nd derivative of f of x. So I have negative n minus 1th derivative of f of x at 0 minus s times the n minus 2nd derivative of f of x at 0 plus s squared times the recursive part of the Laplace transform of the n minus 1th derivative of f of x. And I can just do that to keep on reducing the power of the derivative, because first we had an nth derivative, now we have an n minus 1th derivative in the Laplace transform argument. So I can just keep doing this, and eventually I end up with a nice pattern which may not be quite intuitive at the start. So we've negative s squared the n minus 3rd derivative of f of x at 0 minus minus s to the n minus 1 times the 0th derivative. If we did this n times, 0th derivative is just the function itself at 0, plus this part, the Laplace transform excess part, s to the n Laplace transform of the 0th derivative of f of x, which is just f of x itself. It's just a matter of seeing the pattern. If you don't understand, you can pause the video if you want. Okay, so what I'm gonna do is, we have this nice formula that we can generalize. So the integral from 0 to infinity, I'm just writing the overall expression that we started with, e to the negative sx, the nth derivative of a function of x dx is just, I'm going to write this Laplace transform term out first separately, plus sorry, I should take a minus, right? Yeah. So yeah, minus the sum from I equals 1 to n of s to the I minus 1, the n minus ith derivative of f of x at 0. That's the general form of the Laplace transform of the nth derivative of f of x. Believe it or not, that's the general form. And however small or insignificant or just theoretical mess this may seem, believe me, and mark my words, it's going to be really helpful. So let's look at some examples of applying this on a fresh page. See you there.